Hello everyone. Today we are going to talk about induction. So we use this method to solve many mathematical problems, and it's also useful to prove some theorems. Let's see what is a mathematical induction. So in this method, we are trying to understand whether I can reach a specific step. Assume that you have infinite number of steps, and if we ask, for example, whether I can reach a step number 100, step number 1000, is it possible for me or not? Then in this method, instead of just going through infinite numbers and check whether we can reach it or not, we can use mathematical induction. This is how it works. First, we should find where is my initial step. For example, in this picture, step 1 is my initial step. Then the next thing to do is that if we assume that we can reach step number k, does it imply that I can reach step number k plus 1 or not? If this is true, it means that by considering I have an initial step and then I can reach from k to k plus 1 anywhere in this, for example, series of steps, then in that scenario I can reach any step that I want inside this infinite number of options. So that's the idea about mathematical induction. Instead of checking infinite numbers, just by considering this method, you can solve many problems. Now let's go through it officially. Now consider Pn as a propositional function. We already know what a propositional function is. Then we have this principle of mathematical induction. To prove that Pn is true for all positive integers, so usually we talk about positive integers. It means that natural numbers plus 0, 0, 1, 2, and so on. And sometimes the initial state is not 0 or 1. Maybe it starts from 4, maybe it starts from 10. It depends on the problem. But usually in the standard format, it starts either from 0 or 1. Then we should complete these two steps in order to solve the problem. First step is the basis step. To verify that P1 is true, the first step, it could be P0, it could be P1, it could be P5, the initial step. The next one is the inductive step. We show that the conditional statement Pk implies Pk plus 1 is true for all positive integers k. If we can prove that, then it shows that I can reach any step on my problem. So let me give you some examples. We will also practice it through weekly assignment for sure. And let me talk about it even more later. So anyway, let's start with the example. Show that if n is a positive integer, then this equation holds. So if I want to use mathematical induction, what can I do? The first thing to do is to consider my initial step, basis step. So consider it from 1. It means that the first sentence of this, the left side of the equation. So the first sentence is 1. What about the right side? On the right side, if you insert 1 instead of n, you will have 1 multiply 1 plus 1, which is 2 over 2, which is equal to 1. So this equation is true for the initial step. If you find it, then you can go to the next step, which is the inductive step. So as I said, sometimes we can start it from 1, sometimes 0. It depends. We should check. If you check, for example, for 0 and it doesn't hold, maybe you should go one step forward, and from 1, this is working correctly, and so on. So inductive step. For the inductive hypothesis, we assume that Pk holds for an arbitrary positive integer k. So this is our assumption, Pk. We assume that this is true if I consider k which could be any non-negative integer, and this equation should hold. So we assume that this is true for k. Now, let's say if I assume this is true and I consider it for k plus 1, what happens? So instead of k, now just include k plus 1. So until this statement, this is k plus 1. So for this one, instead of k, just insert k plus 1. So assign k plus 1 inside this one, which is k plus 1. Inside the brackets, we will have k plus 1 plus 1. You see, whenever you see k, just consider k plus 1. And at the end, you will have this expression. So we want to say that whether this is true or not. Okay, so we already done this part, and we are not sure whether this is true or not. Then in our induction hypothesis, we should show it. Now, if I consider k plus 1 added to this one, until this part, 1 plus 2 plus until k, until this part, I know that this is equal to k plus 1 over 2. How do I know that? This is our assumption. We show that this is true, okay? So until this element of the statement, we can say this is true. Plus k plus 1 plus k plus 1. Now, if from here I reach exactly the same expression here, I show that this is true. So by just adding it to this ratio at the end, I will see, yes, this one is exactly the same as this one. So I showed that if I consider this one to be true, it means that 1 plus 2 plus until k is equal to this one. Then I showed, yes, this one is working for me correctly. So that's the way mathematical induction works. Instead of checking all the statements, I can use this method. Let's go through other examples for practice, because induction needs really practice, and we should go through it again and again in order to be powerful. It needs some tricks sometimes to solve each example related to it, so we should be ready for that. And now we will again use the mathematical induction to show this expression is true, this equality. So we start from 1, then I will check it here whether it is working for 1 or 0. This is the thing we should check from the beginning. If I consider 1, it is not the first statement. Even for 0, it works. So 0 is my initial state. So if I consider here 2 power 0 plus 1 minus 1, I will reach 1, which is the first statement of this expression, as you can see. So as I understood, 0 is the initial step for me, and this is my basis step. Now, next thing to do, which is more challenging, is the inductive step. For inductive step, again, I can consider that this is true for k, which is any non-negative integer, and then I should show that this is true also for 2k plus 1. So, I mean for k plus 1, which is inside this expression. Now here, I included the next sentence inside this expression, which is 2n plus 1. Now, instead of n, we inserted k. We assume that this expression is true. So this is our assumption, which is true. Now I add the next statement, which is related to k plus 1 step. Now I should show that that equality holds. So here I can consider until this part, this is exactly the same as what we had for 2k plus 1. And now instead of k, I inserted k plus 1 inside it instead of k. So what I have at the end, 2k plus 2 minus 1. If I reach this statement at the end, I prove that this is true. Exactly the same way we did it for the previous example. So what did I do? I considered the next sentence. Then here, instead of k, I included k plus 1. So we will see here that until this statement, 1 until 2k, I can write it like this. Why is that? Because this is our assumption. Whenever you see IH, it means that induction hypothesis, okay? So until a statement 2k, we can write this because this is our assumption. This is true for k. Now the next one is 2k plus 1. It's like adding 2k plus 1 to each side of the equation. This is exactly the same we did in the previous example. You see, we added the next step to both of the equations. Now here, actually I cannot see what I wrote here because of the tab. Let me change the view. Just a moment. Yes. Now here I have 2k plus 1 minus 1, as I said, because of the assumption, and we will have plus 2k plus 1. Now I can consider this one negative out, the positive in. It means that for addition and subtraction, order doesn't matter, right? I could write 2k plus 1 plus 2 power k plus 1 minus 1. Okay, so I have 2 times of this expression, 2 power k plus 1. So 2 times 2 power k plus 1 minus 1, which is equal to 2k plus 2 minus 1, which is exactly the same as we had in our assumption. So let me continue with the next example. Now, use mathematical induction to prove that 2 power n is less than n factorial. Now, instead of equality, I have less than. For every integer n with n more than 4. So it means that my starting point is not 0, it's not 1, this is 4. So it's given to me from the beginning. So when I want to check it from the basis step, I use it for this initial value, which is 4. So 2 power 4 is less than 4 factorial. And if this condition holds, then this is true for the basis step. So 2 power 4 is 16, and 4 factorial is 24. So 24 is more than 16, and this condition holds. So basis step, there's no problem with it. By the way, whenever we ask you to use mathematical induction, and you find a counterexample, if you find a counterexample which is more than your initial value, it means that you cannot use mathematical induction to prove that theorem or solve that problem. So in that scenario, we should be careful. But anyway, as soon as you find the initial point and there's no counterexample, as much as you check, so it's fine. We can check it for, if it is okay for k, it should be okay for 2k plus 1. Now for this one, assume that I want to right away consider 2 power k plus 1, and I'm already sure that this expression is working for 2 power k less than k factorial for any k. This is our assumption. If we can reach the conclusion at the end that it is working for 2k plus 1 as well, then we have proved it by using mathematical induction. So consider k plus 1 instead of k now. So 2 power k plus 1, you can write it like this. And from the assumption, I know that 2 power k is less than k factorial. So I can say that this expression is less than 2 multiply k factorial. So 2 is exactly the same. But here I know that 2 power k is less than k factorial. So it is true. Next thing to do is to consider k plus 1 is more than 2. Why do I know that? Because we don't know exactly what is k. We know it from the beginning because n is more than 4. So the values that k can take starts from 4. So from this expression, I'm sure that the least value that k can have is 4 And if you add it to something, and if you multiply it again to a number more than 4, so for sure, k plus 1 anyway is more than 2. If it is the least value, this is 4, so 4 plus 1, this is 5, so 5 is more than 2. So any values more than 4 you put for this one, of course, it is more than 2. So you can use it. So whenever you see inequality like this, and you see that you can write the expression which makes your job easier, then you are allowed to do that. It's not the case for equality. For equality, the expression should be exactly the same. But for inequality, we can use these tricks like this one, which is very useful. So what is k plus 1 multiply k factorial? This is k plus 1 factorial altogether. So we have shown that 2k plus 1 is less than this value, okay? Because this equality is for this expression, okay? This one is less than k plus 1 factorial. So what did I do here? By using mathematical induction, first I checked the basis step. I consider 4 as my initial step, and it was working, it is true. Then for inductive step, I consider that 2k less than k factorial. It means that for the k step, this is true. Then by this assumption, I want to show whether this is true for 2 power k plus 1 less than k plus 1 factorial or not. And this is the proof of that. So another type of induction is strong induction. What is different here? Because they are very similar, because it's a type of induction anyway. For this one, for inductive step, you can see that it's not just pk implies pk plus 1. It's the intersection of all the previous possible steps that you could imagine for k before k plus 1. And why we do that? Because it sounds more complicated than just induction. Actually, it's not, because we are talking about intersection, okay? Because if I want to imply from pk to pk plus 1, sometimes it's not that easy. It's not possible to prove it. But if I consider the intersection among all the expressions, then yes, it may be easy for us. You know, you may say, as computer scientists, why do we need to know about proof of, for example, mathematical induction or something like that? And I may agree with you, because I know the applications is more interesting for you. And as you know, for the previous topics, I tried to just focus on the application more than just the theorems. But there is no way we can get out of this. Induction is a part of your syllabus, and it will for sure will appear in your midterm as well. That's why we should get ready for that and practice as much as possible. But for a strong induction, I won't ask it in the midterm, because this topic is not in your syllabus. For application of strong induction, this is very interesting for you guys, because this is a very important application of induction. And for computational geometry, this is a huge course. Usually we offer it to graduate students. And for that, you should know, you should have a good background in computer science and mathematics. For bachelor students, we don't teach this course. But if you know about the induction and after that strong induction, it will be nice to go through these topics anyway. If you are interested, you can go through that and ask me your question. And for this lecture, it's nice to go through the chapter 5.1. If you go through all examples, you will get more powerful about induction. And I suggest you guys to do it during this week. For weekly assignment, I will also give you example about it, and we will solve it together. For 5.2, this is not included in your midterm exam. This is related to strong induction. It's not in the syllabus of your course, but as extra reading, why not? As extra reading, you can read it, and if you have any questions, you can ask me about it. Okay, guys, that was for today. If you have any questions, please let me know. Otherwise, next week we will deal with the weekly assignments related to induction. And also on next Friday, we will talk about recursion.